Today we'll be going through strong induction. So first I'll go through a couple of steps and then we'll go through a practice problem because I think induction and strong induction especially is best understood through practice problems and by doing a lot of them and seeing how they work. So strong induction is pretty similar to mathematical induction. Now the key difference is in the basis step and the induction steps, but it has a lot of the similar kind of structure. So the goal again is P of n. So we want to prove something is true always. Now, step one is going to be, again, the basis step, like mathematical induction. So the key difference is we might have more than one. So we're going to use a to represent some integer here, just to say that mathematical induction can have more than one. So here, maybe it's like 3 or 4 claims. Now, step 2 is the induction step. Now, the key difference here is you're going to assume the kth level, but you're also going to assume everything up to the kth level too. Now, the way we express that is through this index I. So we're going to assume P of I for 1, or in this case, a, so whatever that integer up here is less than or equal to I, which is less than or equal to k, which is to say I can be any of these values between your basis step and the kth level. So it's just everything up to k. And then with that, you prove k plus 1. Okay, so let's go through a practice problem. So just to see how this works, we can go through an example where we want to get a of 3. Now if we look at our formula, we see that a of 3 is equal to a of 1 plus 2 of a of 2. So a of 1 plus 2 of a of 2. In this problem they gave us a of 1 and a of 2, otherwise we wouldn't be able to start the formula. So that means a of 3 is 1 plus 2 times 3, which is 7, which is odd. So the goal of this proof is to prove that this is always odd. Okay, so let's start with our steps from before. We have step 1, which is our basis step. So in our basis step, we can look at what we used up here. We used A1 and A2, and without A1 and A2, you can't start the problem. So those are just going to be our basis steps. It's going to be A1 is equal to 1, and A2 is equal to 3. And because they gave it to us, we don't actually have to do any math. We just have to look at those and say, look, 1 and 3 are odd. And we can prove that by definition of odd if we had more time, but you get the point. Great. Now, step 2 is our big one, where we're going to do the induction step. Okay, so we're going to assume value a of I is odd for 1 is less than or equal to I, less than or equal to k. Awesome. And now we want to try and do a of k plus 1. Now from our formula, we know that that's equal to a of k minus 2, sorry, a of k minus 1, because this is plus 1, plus 2 a of k. And from our inductive step up here, where we assumed a of I for this range, these both fall within that range, which means these are just both odd. Now, the important phrase to use here, which you always have to put down, is by inductive hypothesis. Because we're using our assumption to plug in something different here. So always put down by inductive hypothesis when you use the assumption you make. Now, if we replace those with some filler variables, and these are by definition of odd, how an odd integer is represented, P and Q are integers. And if we rearrange that with some algebra, you can work through yourself. What does this look like? Well, it looks like the definition of an integer. And to make it more clear, here's it rearranged, where this is just becoming y, and y is again an integer. And this is for ak plus 1. So if we look at that, we see that ak plus 1, by definition of odd here, is always going to be an odd number.